Okay, so we've got an interesting question here. It says, consider the function f of x equals x squared plus 2x plus 3. And then we've got two approximations of the gradient. So we've got this one here, f dash of x is approximately equal to f of a plus h minus f of a all over h. And the other one is f dash of x is approximately equal to f of a plus h minus f of a minus h all over 2h. And our job is to determine which of the following approximations of the derivative is better at some point x equals a. So that's our job. We're going to decide if this is a better approximation. This should hopefully look familiar over here because this is essentially first principles without the limit as h approaches 0. But in this question, we're talking about h, a small h, or getting h to be small. And this one here might be less familiar, but this I think is called the central difference theorem. And you might see why that's the case when we look at this diagram in a little bit. Okay, so let's jump into it. What we're going to do is we're going to apply this approximation to this function. So let's see what that looks like. Wherever there is an x, we're going to put a plus h for the first part, and then we're going to take away the function, substituting in a. So we're going to get this, which looks a bit messy. It's actually not too bad. You can pause the video and crunch the numbers if you like. You just have to expand, collect some like terms, and what you'll get is hopefully this, 2ah plus h squared plus 2 all over h. And, take h out as a factor of the numerator. You get h times 2a plus h plus 2. Cancel the h's down. And you're left with this, f dash of x being 2a plus 2 plus h. Okay, now let's think about what's going on this diagram here for that. If you think about it, what we're doing is we're taking basically finding the slope of a tangent line between f of a plus h, and let me just change my diagram here for a second. Basically taking the gradient, we're trying to find the gradient of a line between a and f of a plus h, and that's what that represents there. So let's put that line in. It's going to look something like that. And basically, as h gets small, that's changing a, we want to change h. As h gets small, we can see that this line gets closer to approximating the gradient at a. Okay, and we're just ignoring this part for now. You'll see why that's there in a minute. But you can see, as h gets really small, gets closer to a, that gradient of that line approaches the gradient of the function at a. Okay, so let's put that back there. Let's have a look at this gradient. Let's have a look at this approximation over here, see what happens. Again, you're going to get this beast of a numerator, substituting in f of a plus h minus f of a minus h, where this is your function, all over 2h. That's my error. And you get that. It simplifies to that a little bit. Okay, just some changes on the fly there. I made an error. So if, you crunch the numbers on this numerator here, it should simplify to 4ah plus 4h all over 2h. Take the 2h out as a factor, you're left with 2a plus 2. And those lines are repeats of one another, as you can see, but that's all right. And anyway, the 2h's cancel out, you're left with 2a plus 2. All right. So what we can think about now is what this approximation is talking about. It's basically taking the gradient between f of a plus h and a minus h. Okay, so if we put that line in, it's going to be a line between here and here now. Okay, and now we're dividing by 2h. Now, you're probably wondering what the 2h comes from. Remember, this distance from here to here is h. If here is a minus h and here is a, then this distance between here is h. And then from a to a plus h is also a distance of h. So, you're doing y2 minus y1 over x2 minus x1. It's sort of thinking about it in terms of simple gradient type situation. Okay, and so you get that. Now the question is, which of these approximations is better? So let's have a look. It might be obvious actually from these rules which one's better. This one gives us 2a plus 2 plus h. This has got a plus h at the end, which means that h isn't 0. H might be small, but it's not 0. So this, you can probably see, is actually going to be a worse approximation. This will actually be a better approximation, because if we actually think about the derivative of the entire function, that's just f dash x. The derivative is just 2x plus 2. And, this approximation, as it said in the question, is actually the exact derivative at a. Because, yeah, you can see that a has just replaced x there. Okay, so let's actually look at the diagram and see if we can see which y it's better. So if we change h to be small, so h is getting smaller and smaller and smaller. Now our question is, which line, this line or this line is a better approximation of the gradient as h gets smaller? It's a bit hard to see, but if I zoom in, you might see that the line on the top all the time is actually is a better approximation of the gradient. You can see that this line here is a better approximation of the gradient than the line underneath it, because because of the maths obviously worked out that way. But you can also sort of see that, the slope of that line is a bit better than the other one. If we're trying to approximate the gradient at some point A, and then obviously they all come together when h is 0. But yeah, you can sort of see, that this is a better approximation than this line at A. So, and the math sort of showed that. Bit tricky to show on a screen, but hopefully you can see why that second approximation is a little bit better, both algebraically and graphically. So hopefully that clarifies that question a bit. I think it's a nice application of differentiation. So good luck with studying.